Yeah, so last week, so we started took ourselves through a couple of options that are usually used for evaluating machine learning models. That is, what are the options that are available for us when we want to build our machine learning model to be able to check the generalization ability. So we went through the concept of empirical error, which we said could be either regression or classification. We also discussed the inductive learning hypothesis, which is actually the basis for the idea of evaluating the performance of machine learning algorithm or the model once it is built. So, and we said that this is actually almost the most important theory that surrounds the concept of learning, which says if the hypothesis works for enough data, then it will work on new examples. So that once you want to build model, the commonest form of model building is the one we call the supervised learning. So to quickly refresh our brain, we know that we have supervised and we have the unsupervised. The unsupervised learning. So the unsupervised learning is more challenging. We only do it when we don't have option or when we don't have the output. So because of the complexity that is involved, and then the very lower possibility of getting really accurate results. However, what we always wish to have is the supervised, because even the supervised one, which is where we have the input and we have output given to us. So we are not really even sure of, are we able to train a system that can be able to predict when new data comes in? So when you don't even have the output, it becomes very challenging. So which we are going to also look at later, because there are situations whereby we need to use unsupervised learning to perhaps even prepare our data. We can use it as a pre-processing idea to the main supervised learning in some cases. So to determine, maybe to be able to extract some data automatically from the system. However, for the supervised learning we're talking about, this is the inductive learning hypothesis, that if the hypothesis works for enough data, so which means we need to have a way of dividing our data appropriately, which is the basis of what we discussed last week. And then, so this way we just reverse what we did, and then we had more that we were not able to cover appropriately. So it says if the hypothesis works for enough data, so we now say that, let's say I have like 1,000 data samples were given to me. So I divided into 70% for training and 30% for testing. So this step 70%, I'm going to expose the system to both the input and the output. I will say, okay, this is sample one. Then the output of sample one is 1, which means diabetes. For sample 2, the output is 0, which is non-diabetes. For sample 3, the output is 1. And then continuously like that until I expose my algorithm to all the available 70% of that 1,000 samples, which is going to be 700 data samples. After doing that, then I need to check the generalization ability. That is, this is what we are talking about. In this 30%, we are hiding away from the model, from the system. It is unseen. We didn't show the output to it. So we now give it one by one. Now, if the hypothesis works for enough data. So now, if for this data, this 700 we have exposed our system to, we try again to check, is it able to recognize what I have exposed it to? So we can give back these 700 again, one after the other. But this time around, we will not be given the output. We only give the system. Now, since you have trained yourself, then can you check what you have seen before? So we give you sample 1, sample 2, up to 700. And then we try to see what is the accuracy. Is he able to correctly identify what it has seen before? So maybe it's getting like 99% accuracy. Wow, looks good, looks great. But we told ourselves, you don't celebrate at this point, but rather we need to check with this unseen data. We want to see, then it will work on new examples. This new example that we are keeping secretly away, yeah, this is getting 99% of what it has seen before. Sometimes it's not all training set that you get your model to predict excellently well. sometimes your model might be predicting with 50% accuracy. Now, if you have seen some sample data and you are and the system is getting only 50%, this might tell you that, wow, there might be a problem with our system, because if what it has seen is not able to recognize it with high accuracy, how can you guarantee that the unseen one is going to work? That's why we said if hypothesis works for enough data. So that's why we usually want to see very good result. Okay, it's getting 88% accuracy, 95, 99, or sometimes 100%. It means it's able to achieve, to understand all what it has seen before. It's a good move to start. However, we don't celebrate until we go and check for the second stage, which is how much are you going to perform on the unseen data? So this is when we are going to bring in this 30. We now say, now, since you are doing fine with the one you have seen before, now we're going to give you this sample 1 up to 30, up to 300 out of 1,000. 30% is going to be 300. Can you tell us, is this sample diabetes or not? So it's going to predict, no, this is not diabetes, this is diabetes, non-diabetes, diabetes. So since we know, we already knew the outcome ourselves, but we kept it secret from the machine. So we now try to compare the prediction of this hypothesis with the original output of this unseen data that we are aware of. So we now see how they are performing. Now, so we try to see how far can it go. Let's say, for example, it's able to get on the testing set, it's able to get like on the training set, it's getting 99% accuracy. On the testing set, the unseen data we just exposed it to, the input, is getting like 85% accuracy. This is good. This is good. This is very okay. This is okay. See, however, we might need to go for improvement later, but there's no cause for alarm at this level. Or maybe it's getting 95. Wow, excellent. Training set that it has seen before, 99%. The one that is not yet, has never been seen before, 95%. That's good. That's a good start. However, when you train a system and then you share the training performance and it's giving you 99%, but when you have the testing performance, it's giving you 40%. This is a no-no. We call this overfitting. Overfitting. It means your system has only succeeded in memorizing the training set. So we want the difference between the training performance and the testing performance to be very small. So when you're getting 99% accuracy and getting 40% in testing, this is a no-no. In fact, I prefer that you get 85% in your training and then you get 75% in testing. This is good to start. So it's better for you not to get 99, but you are getting something reasonable here, because this is the main concern, that we want you to be able to perform on unseen data. So that was what led us to the idea of generalization. So during the training, this is what we give to you. See, can you see this? This is an apple, this is pear, this is tomato. Once you train, then later we show you again and try to let you recognize what you have seen before. But then we don't celebrate even if you are getting 100% at that level. We only celebrate if we now give you, these are the ones that have never been seen before. We give you this. Are you able to tell us this is apple? This is pear, this is tomato. You identify all of them. Maybe you only miss one out of 1, 2, 3, 4, 5, 6. Out of 6, it's missing one. That is excellent performance. So this is the idea of the inductive learning hypothesis, that if you really work well on the training set, you should be able to work on the unseen data set. Now, we now say, how do we prepare the data set? We now say there are 2 major ways, and we summarized it for us last time, that you can have division into 3 parts: training set, validation set, and testing set. And then we can have division into only 2 parts, the one I just used as an example now, 75%, 25%, or 70%, 30%, or 80%, 20%. It's flexible. See, even some of you go as low as I'm using 60%, 40% for testing. But however, it's recommended that the training set should be more than the testing set, because you need the system to be exposed to as many as possible known samples to be able to increase the generalization capability. So these two partitioning methods, we call them holdout method. Holdout method. Holdout means you expose the machine to one part of the data and you hold out. You keep the rest away from the system. That is called holdout method. And the holdout method could be two types. Division to three parts, training set, validation set, and testing set. And I strongly recommended this for us, especially if your data set is huge. You see, you have 20,000, 15,000, 2,500 samples. You can afford to have division into three parts, because that will save you from any criticism that might come from people so much believe in this. There are some reviewers, they are so fanatic about this three partitioning, even though it shouldn't be. This two partition is also correct. See, it's correct theoretically and practically. But there's some people who are really they're fanatical about three. If you don't use three, they're gonna criticize you. You need to understand how to write appropriate rebuttal for them before you can get your work through in the review process. So if your data is big, divide it into three sets. Use the first one for training. It could be like, you could use like 70% for training, 15 for validation, another 15 for the final testing or publication set. But if your data is not big enough, then division into two is okay, as we have explained. Then the second one is the one we call the resampling or the n-fold cross validation. So which is where we were before we ended the topic the other time. So we described the four sets where you just divide your data into two or into three, as the case may be. So, and then we describe with appropriate the grammatical presentation. This is where you divide it into three. You see, here you divide it into two only. This is your data set. You divide it into training set and testing set. After building the model, use the testing set to check. This is final. So why the second one say, okay, no, I divide it into three. So before the data even gets into the building process, we divide it into two. The testing set is outside here, waiting for us to call it later after the successful building of the model. While the one inside here, we subdivide it again into training set and testing and validation set, build the model, use validation set to check it if it is fine. You see? So why then finally you use the one that you kept here, you use it to actually check the final predictive evaluation. This is fine. Some people only have opportunity of doing the one inside only, this one only. You see, divided into training and testing and validation, which is also fine. So this is under the holdout method, as the case may be. As the case may be. Now, so and then next we briefly describe what we describe now is known as the repeated holdouts. So I mean, it's the holdout method. However, some people do come up with the idea of repeated holdout, whereby you run division into 70 to 30. You divide your data into 70 and 30 randomly. So during the first division, you get the accuracy. You do it again, 70%. Since it's random, some data that participated in the testing set, they might become part of the training set. This is what we mean by repeated holdout. You keep doing that for maybe 10 times or 100 times, depending on the problem you are solving. And then you find the average of the result to see how it is working. But rather than doing this, so it is recommended that you can always go for the n-fold cross validation method, which was the one we described yesterday. And then we did explain that, okay, here, you use this for validation set. These are the training set. The next phase, what was part of you take part of the training set before now to become the validation set. It means every data set will participate in validating the data, in validating the model. So this is the idea of the cross-validation data partitioning. It has advantages. Some people so much believe in it, but however, if your data is huge, then it doesn't go. Just divide your data into three and use the holdout method. Because for big data, if you are going to use cross-validation, that's going to take a lot of time And practically, there's really no need to go for that. See, when your data is very few, cross-validation is recommended. But when you have huge data, go for holdout method. And the 10-fold cross-validation is very popular. It can be 5-fold, it can be 3-fold. So, but the 10-fold is very popular. The practical implication of how it works is, this is the full partitioning of the data. You divide the data into 10 of equal sizes. Let's say you have like 1,000 samples, divide into 10, each of them is going to have 100. So I use the first one to test my model, while all the others are combined as training set. In the next stage, I go to the next step. This one becomes the testing set. I keep moving the window until each and every partition window is used as the testing set. And then we presented it, and we also mentioned that we have the special type, which we call the stratified cross-validation. Why do we need stratified cross-validation? This is that when we are dividing the data, because of to avoid the problem of imbalanced data set, we don't want to run into the problem of imbalanced data set. We advise that when we are breaking the data into portions, we want to ensure that the portions are also balanced. Imagine I have 1,000 data sets, so 1,000 sample. So when I divide into 10 portions, there will be 100, 100, 100 in 10 places. Good. But when I want to partition this 100, 100, 100, I want to make sure that since this one is made up of 500 class A, and then 500 class B. Now, so what we want to be sure of is, if I divide this 500 class A, 500 class B into 10 portions of the 10-fold cross-validation, I want to have here 50 class A, 50 class B, 50 class A, 50 class B, making 100 in each fold. So ensuring that is what we refer to as stratify. Stratify, that is the partitioning of the data into subfolds must have the same equal number of classes. Why? Because if you don't have equal number of classes, then the problem of imbalanced data is going to come. The problem of imbalanced data is going to come. Yeah. So if you don't have use this cross-validation, the stratified cross-validation, then you end up having something like, maybe here you have 70 for A, and then you have 30 for B. You can see the red one is the B, the gray one is A. It's even possible you might even have 99A and 1B. And maybe in another case, you might even have 100A and 0B, which is very bad for the modeling. Because we want every class you want to model to be well represented in each of the folds. Because as you know, each fold will be used for testing set one time. This one will be used for testing set one time, up to 10 training testing set. So now it means if I have a fold here that is having 0 class B, that means class B is not well represented. So there's going to be a bias towards the class A that takes the majority. So this is the idea of stratified cross-validation. You see, usually, originally, if your data is not balanced, it's not a good thing. It's not a good thing. One of the recommended things is to first of all try to balance your data in the pre-processing stage by making sure your data is balanced. But when you talk of balancing, if you have like maybe 400 class A and 600 class B, this is still fine. It's okay, it's manageable. It is when the size is becoming abnormally too far apart. Like class A is just having 85, and class B is having like 525 or something like that. That is huge difference, because there will be a bias towards class B. And this is a normal thing we have in our data set. Because if maybe you are looking for people who are diabetes, you go to a clinic, the population of people that are not diabetes will be more than those that are diabetes. So which means the negative class will be more than the positive class. So it might make your system to be biased towards the non-diabetes people. You see, which could also be dangerous, because it means it could be predicting diabetes people and not diabetes, which is a very critical mistake in medical prediction, as we discussed earlier, and we still have opportunity also to revisit that one more time, inshallah. Now, So, but let's say you have your data that is balanced already, then how can you afford to now destroy that balanced data during the cross-validation partitioning? So that is why we opt for the stratified cross-validation, which is a special type of cross-validation for us to take note. Now, another special type of cross-validation is the one we call leave one out cross-validation. Leave one out. So we couldn't get to this point last time. So leave one cross-validation. What is leave one out? I mentioned earlier that cross-validation is often used when your data set is very few. When you have very few data samples, then you go for cross-validation. But when the data is really, really few, like imagine you have, like I have seen people invited me for possibility to model, and they said the only data set they have is just 12. They have only 12 samples. So tell me, for 12 samples, how do you divide the data? I cannot use holdouts, because holdout means I want to use like 8 for training and only 4 for testing. No, this is going to be too abnormally small. Now, how do we do it? I go for 10-fold cross-validation. How do you divide 12 samples to 10 places? That is average of 1-1. So it doesn't make any sense to do that. So in that case, we opt for what we call leave one out cross-validation. See, holdout does not work. Even the standard cross-validation will not work. So we go for leave one out cross-validation. And what is leave one out? In leave one out, every sample is going to be taken as validation set at least once. See, this is a representation of leave one out cross-validation. This is how it works. So I have only, let's say I have like let's say my N here, maybe my N here is maybe 21. It can even be 45. Even at 45 or so, dividing 45, let's say we should have 50. You want to divide 50 into 10 places. That makes each one will be having 5 samples. It's still very small. It is considered small. So in that case, you just go for like leave one out cross-validation, whereby, or let's say our N is 12 as the example. So you take this one as the testing set. This is going to be for testing. You keep it outside. Then you use all the remaining data for training. Once you train, you test on this. Then the next, you shift your window to 2. You add this one back to the training pool. And then you use this plus everything for training. And then you check the performance with this. Then you shift the window. You return this one to the training pool again. You keep doing that until you have the last sample here, which is number N, as the testing or validation sample. So it means what we're trying to do here, we want to expose all the data set, all the data sample to be used for testing, so that we can be sure that at least this model, how is it going to perform in this kind of an environment? And often than not, we do use this kind of model evaluation scheme to develop what we call proof of concept. Proof of concept. Because you cannot deploy it for a client. You can't train something like this and deploy it to your client. Usually it's just a proof of concept that is it going to work? If we have enough data later, can it work? Then we can then try to see, okay, it's going to work or it's not going to work. So we use it to check. This is why some researchers would usually like it, even though some of them don't, perhaps some of them are forgotten or they are not aware that you use cross-validation when the data is very small. So you see someone have maybe huge data like 3,000 samples, then he decided to divide it into 3, training, testing, and validation. You still see reviewers saying, but why don't you use cross-validation? Why the need for cross-validation? If something is working on the holdout method, that is fine. See, so because some of them may want to show concern that, okay, maybe the partition you use is just random. So that is why sometimes I do advise people, okay, to avoid this kind of reviewers' concern, you can use cross-validation, one side. Let's see the performance on the cross-validation, report the result, but go ahead with the holdout method. Because holdout method is the actual model building system that you can deploy for your client. If your client, somebody, a company asks you to come and develop machine learning system for them, you cannot deploy a cross-validation model for them. You need a model that is trained on enough data, like out of 2,500, I use like 1,700 for training. I use another 600 for validation and another 300 to check it again before I finally deploy it for my client. This is how the deployment system will work in machine learning system. But for cross-validation, we use it for proof of concept to really show to the company, maybe a company wants to develop a system, and then they say, okay, we only have 16 data samples. Okay, let's use it we can use cross-validation to check proof of concept. Maybe it's going to work. So maybe by the time we develop, maybe leave one out, as I've explained, we were able to get like 99% accuracy on that data. Wow, that would be good news for that company. So we can then talk to the company that, wow, your data has a very good output, or it has a very good prospect. So we encourage you to spend money to go and gather data similar to what you have brought. Then the company now know that since we have given the feedback that what we have achieved is encouraging, then they can deploy funds to raise data set, to go and gather enough data set. Then we now go and develop the holdout method for them. Maybe they're able to now raise like 5,000 samples. We can now divide it, 3,000 for training, 1,000 for validation, another 1,000 for testing, and then we can release it for the company to be used for their future predictions. So this is how you see the way you look at cross-validation and holdout method. So the leave one out is used for the special case whereby the data is extremely few. We see have it. Except for very few cases, for example, later we're going to talk algorithms like support vector machine. It's a very unique machine learning algorithm that is able to work in the presence of few data sets. Because majority of algorithm, when you have like, somebody have like 16 samples, and you want to divide it into maybe this 26 sample, you want to divide it into like 20, maybe it's 15 for training or 18 for training set, and the remaining 8 for test. Most algorithm will not work because the data is too small. However, support vector machine has proven that because of some of the unique attributes it has, which we are going to discuss later, it's able to bypass this disadvantage and take advantage of, even with 8 training samples, it can get excellent results from some of our experience with areas where the data set are really very few to get. But again, we cannot use it, we cannot generalize it, because what is common to majority of the machine learning algorithm is you need sizable number of data. And like the inductive learning hypothesis we discussed earlier says, if it works on enough data, then it will work on unseen data. You see, the word here is enough. Now the question is, what is enough? It depends on the field. What is enough for medical field might not be enough for civil engineering field. It might not be enough for another field. So that is enough. It's like a fuzzy term there that is subjective. And that is why we always say that let the data speak. Let the data speak. Because people do ask me when I make this kind of lecture, Doctor, what can you recommend as the minimum data samples before you can develop machine learning model? And I say there's no minimum and there's no maximum. But the more you get, the better. What is that definition of the more? It depends on the area you are modeling. It depends on the kind of data you have. In some area, you might have 1,000 data set and you are not getting any reasonable results because the data is noisy, it's very bad. They are not well correlated data. And somebody might just be able to get just 300 and you could be getting very, very fantastic results. So that is why you always remember the principle, let the data speak. So that is on cross-validation, and then leave one out as special case of cross-validation method. Then there is of course, we have the generalized form of the cross-validation, so which people call the VFold cross-validation. For example, your V can be equal to 10, can be equal to any number. How does it work? You randomly partition the full data set into V disjoint subset, each roughly of size n divided by V. That is, we want each of the partition in the fold should be roughly of the same size. Sometimes you might not get the same size because we need to be very realistic. Like the sample given here, see, you cannot always be sure that, okay, let's say each of them is 100, 100. Some might be 99, maybe 95. I mean, the number of data, because you cannot always get, you will not always get like 1,000 samples exactly. What if you have 965 as the number of samples? So, and you divide it into 10. So you're going to have like 96.5 per, and you don't divide data, there's no 0.5 data. Everything has to be whole. In that case, you see, one of these partition might be more than the other by 1 or 2. It's okay. That is why we say here in the generalized formula, they are each roughly of size n divided by m. See, roughly of the same size. It doesn't mean it has to be the same size as a must, because in reality, data sets don't work that way. So then you set up a loop here, a repetitive system for I is equal to 1 to 10. If you choose to use 10, you can also use 5. Let's say if your data set is not much, very few data, you can use the food UB5. Recently, we share experience based on every day you have experiences with reviewers. As researchers, we do share experience on this point. Recently, there was some of our students actually were to get their work published. One of the reviewers, 3 reviewers, 2 of them accepted the paper already. The remaining one, he insisted that while the students should use 10-fold cross-validation, he said the data is not much. He now insisted that they should use 5-fold or 3-fold. I think he recommended 3-fold, that they should divide into 3-fold since the data is small. It makes a little bit of sense, but then from my experience, it doesn't make much difference. But then since he insisted after 2 revision cycles, he still insisted they need to do it. I said, okay, student, do this. And then the results showed that actually there was no really big difference, because after the 3-fold, there are like 4 different data samples. It may be in part of the data set, 3-fold was getting better result than 10-fold. In another part of the data set, 10-fold was getting better result than 3-fold. So then they concluded that, so using 3-fold doesn't make any big difference in what they have done earlier on. So these kind of things happen, but then that's why sometimes I do ask people, try different options, use 5-fold, report your result, use 10-fold, report your result, compare them a little bit and move on. That saves you some very picky reviewers from setting you back at some point in time. But these are letting you know some of the realities and possibilities that we might face when you implement your evaluation systems. So once you set up the loop, so it could be 10, it could be 5, it could be 3, as the case may be. So you train on the 90% of the data, that is, you keep 1% away if you are using 10-fold. 90% for training, and then you check the accuracy on 10%. The remaining 10%, you check the accuracy. In the next run, this 10% will become part of the training. You remove another 10% from the training to make it to be the test. And then you're going to do it repeatedly for I until your I is equal to the maximum here, which could be 10 or 5 or 3, as the case may be. Now, the final cross-validation accuracy is going to be the total, or the accuracy you are getting for each one. You find the summation divided by the total number you have used, either 5 or 10. That will give you the average of the result. So you show the method with the highest cross-validation accuracy. It's a common value that people often use 5 and 10, but then there's nothing really fixed. Like I said, one of those reviewers insisted they have to implement for 3. And then they did it, and then there was no really big difference. Now, that is using the generalized, we call it VFold cross-validation, when you have to generalize the idea of cross-validation method. But take note, when your data is sensibly okay, you go for holdout method. Holdout method, whereby you can divide it into 3 parts or 2 parts, as the case may be, depending on the size. Although you go for the cross-validation, which has different method, different specialized term, like stratified sampling, which is good for everybody to do. Leave one out, whereby you're going to be using 1 by 1. This is when the data is extremely very, very few in number. So, and some a couple points on the cross-validation, as we've mentioned. Some of the challenges with cross-validation said, note that cross-validation generates an approximate estimate of how well the learned model will do on unseen data. This is the issue. approximate. You see, this is why we say they use it for proof of concept, just to check if this data is going to work fine. Then, if it's going to work fine, if there is good prospect, we can then ask the client to go and look for more data, and we can build the appropriate model using Holdout method. So by averaging over different partitions, it is more robust than just a single train validate partition of the data. So this is the opinion of those people that support cross-validation. They believe that by using that cross-validation, that every part of the data participate in testing and training, you can be able to really see how well the data is going to perform. So the generalized form is known as the VFold as described. Now, another point to take note is that the VFold cross-validation is approximately 3 times computationally more expensive than just fitting a model to all the data. This is one of the disadvantages of cross-validation, because you are going to repeat it V time. It could be 10, it could be 5. Imagine you have data that is up to like 15,000 samples. So you're going to partition it into 10, and then you have to repeat the experiment 10 times, which is going to add a lot of computational complexity to your system. Which is going to have a lot of, so one of the major problems of cross-validation is it is computationally more expensive. And that is the reason why you only go for it if your data set is small. So when the data set is big, it's a no-no area. Now, I say, however, for deployment to client, Holdout method is the appropriate option to use. I think I've explained this. When you want to deploy your model outcome for your client to use in their site, then the Holdout method is going to be the one you are going to use. Yeah. So realistically, VFold cross-validation is advisable when the data set is very small. And these are some of the take-home points that we have to take note very much when we are evaluating or building our model. The last but not the least, I will mention briefly is the one we call the bootstrapping. Bootstrapping. The cross-validation we'll be discussing, they use what we call sampling without replacement. It means a particular sample cannot appear 2 times in the cross-validation. No, it's not possible. That's why we said, if you have 1,000 data sample, 100 samples, you divide it into 10, each partition will have 10, 10, 10, 10. So there's no sample that can repeat itself, being A and being A. No, once you partition it at once, 10 partitions, you can only repeat 1 time. However, Bootstrap uses sampling with replacement, and this is often needed in Ensemble. If you go back to watch some of our Ensemble videos, you see that we mentioned Bootstrap repeatedly there several times. So because sometimes you need to repeat some samples, maybe those samples, they are very unique. Some samples are very troublesome. They're difficult for the machine learning algorithm to recognize them. We repeat this kind of samples so that the machine learning can get used to them. We do this sometimes when we develop ensemble techniques. You see, especially in the boosting approach. At the first stage, we develop the first algorithm, the first model. We check the performance. Those samples that are being mistakenly classified, we increase their presence in the next stage. For example, if sample 2 is not being correctly classified, we make it come out and repeat in the next partitioning like 3 times or 4 times or more. The same sample, we repeat it. It's like forcing the machine learning algorithm to, either you like it or not, you are going to understand this data by force. This is the idea of bootstrapping. It has its own advantages, and there are situations where we use, especially when you want to build ensemble. So here you sample data on n instance n times with replacement. So sampling with replacement. A mathematician knows better on this. When you sample with replacement and we sample without replacement. So sample with replacement means that every time you choose a data to be used, that data still have the same equal probability to be selected like any other person, but because you are replacing it back. So a sample could be picked like 10 times without picking another sample for the modeling. So then these data are used for the training, and the instance from the original data side don't occur in the new training set for testing. Some sample could be deliberately or systematically edged out of because we already know the system already correctly classifies a sample. So we don't need that sample. The one that the system doesn't understand is what we need to expose the system to. This is the idea of bootstrapping. So this is an example. You have the original data set here, and then You have the first bootstrap. You can see the first bootstrap 1. You can see here, these are the samples, data sample up to 10. You can see X8, X6, X2, X9. You can see 8 is repeated twice. See, you can see X4, X8 again, even 3 times. X2 also is repeated. Meanwhile, X3, X7, and X10, they are never mentioned. So we use this one for testing. We use this for training. The next time again you build it, you see 10 is part of it here. Some are repeated. Those that are not repeated in the sampling, we use them for testing. You can keep doing that as many times as you want. This is what we call the bootstrap method of evaluating model or building model. It's not a popular one, and it's not generally used, but we use it when we think it's going to benefit, especially when we are building ensemble techniques. Because ensemble techniques try to do a lot of manipulation towards generating different models that they will combine together to make voting that can hopefully give us a better accuracy. So I think that is all we're going to have for now regarding the idea of evaluating model. How do we build our model? And then which one is better? When do we use each of them? So Holdouts, use if your data is big, is enough. And then for also deployment for your client, you use it. Cross-validation, you use for proof of concept. So whereby you just need to see quickly how the data is doing in each of them, depending on where the issue really comes up from. So this is what we're going to have for the day. So really wish you all the best, and I hope we've benefited to some level. So thank you very much for attending. And then if there's a question now, we go to question time. We'll take a couple of questions before we call it a day. So Barakallahu Fik. So thank you very much. Assalamu alaikum.